extending our idea of volume balance of revolution, I want to consider this question here.
Number 9.
Are you have a specific one?
I could figure all of them out except for 9. Maybe just didn't because I was tired.
Yeah, the last one.
That's highly possible.
I figured out 10. Like,
I could not get 10 today.
in 10, I had to figure out a certain trig identity that I didn't know. So good.
Yeah, the last two,
But I
they were
didn't.
hard, and I was
That's
like,
probably why I
You know
couldn't
it
get
now.
that one.
Relative. I know it now. Will I remember it? That's all. This is why I was going to page 46.
I know the science squared one by heart now.
That's 7 times 3.
No, it's the equal science squared.
Are you?
Okay.
No.
I
Do I
couldn't figure
care?
out 9. I kept getting a different answer. And 10, I only figured out because of Google.
X equals.
what you guys like in the galaxy?
That one we can't see
You can do 9 first.
So,
I'll put that back to 7.
Be like, oh, that's it, let's go. Doesn't matter, it could be red.
like pasta, I was like, and then you I was like, I rolled over to 755.
My dad, okay, so every day this week.
All right. So the question is, do we choose X's or Y's? Actually, no, that's not even a question. We're revolving about the Y-axis, right? And so since we're revolving about the Y-axis, we must do a cut parallel to the Y-axis, and we have a representative rectangle dy, just like so. And so we have, the setup is fairly simple. We're going to have an outside radius. And that outside radius is going to be curve minus axis, which is going to be tan pi over 4 y minus 0. And so now we have volume equals pi times the integral from the first y to the last y of r squared dy. And there we go. So now we look at this and we consider how to integrate this. I don't have directly any antiderivative that involves tan squared. So my next thought is perhaps I can use a trig identity to whip this into shape.
This one I
Science squared equals
And so I run through my catalog of trig identities, possibly sine squared over cosine squared. Then I consider this right here, and I don't like it very much because, for example, if I let u equal the entire denominator right there, then du is definitely not sine squared. Yes, there we go. So I remember my second Pythagorean identity, which is that tan squared plus 1 is equal to secant squared, or like so. And now I do actually have an antiderivative for secant squared, and of course I have an antiderivative for 1, and the game is 1.
Yeah, I got to that. I just kept getting a differential from the back of the book.
No, well,
I don't know.
we got to remember repair for the first integral.
Yeah.
So we're going to get 4 over pi tangent pi over 4y for the first one. And we're going to get y for the next one. And all of that is times pi from 0 to 1. And this is going to give me 4 times tangent of pi over 4. Tangent of pi over 4 is 1. Minus 1. Minus 1 pi. And then all of that minus 0 minus 0. So I get that.
I messed up something. Apparently it's algebra.
Alex brings up a good point, which is, what about those trig identities? And what we discover is that having specific knowledge of your trig identities makes them available to you as go-to tools. And failing to have specific knowledge of those trig identities makes them unavailable to you, which means it's one more play you can't run. You know what I mean? Okay. So how do we get specific knowledge of those trig identities? Well, we're going to start by organizing them. They fall into three categories. The first category are the ratio identities. The second category are the Pythagorean identities. And the third category are the angle addition identities. The ratio identities are mainly a matter of definition, and you guys are all familiar with tangent of x is equal to sine x over cosine x. Cotangent of x is equal to, and I'll let you fill in the blanks if you know these. Secant x equals, cosecant x equals, and finally, the last one is that cotangent x is the same as 1 over tangent x, where we're suitably defined. These guys are all very familiar to you, and because they are familiar to you, then they are actually tools that I see you use on a regular basis, right? You know to use them. You're confronted with cotangent, and bam, you immediately go to cosine over sine if needed. The Pythagorean identities, everybody likes the first one. And then they blow off the other two, and that's a mistake. Because the other two are very useful, as we just saw them. The way to remember all three of them is to see them as all related to the same one, which is this one right here. I can take this guy and divide both sides by cosine squared, and if I do, then I get tangent squared plus 1 equals secant squared. Or I could take both sides of this and divide it by sine squared and get the third identity, which I'm going to let you do on your own so that you see it, so that you remember it. Granted that this is not a proof, it's Euler math, right? I'm throwing symbols around without worrying about things like dividing by 0. Still in all, Euler math is a great way to get started. The angle addition identities are the ones that people don't tend to remember, and that's unfortunate. Maybe I'll do a video next week for the proofs of these, so that you can remember them. But we're going to just take as a given that these guys operate like so, and like so. Okay? And from this, we can immediately generate the subtraction identities by remembering that sine is an odd function, cosine is an even function. So that when I plug in negative y into this one and this one, I get cosine y for that one, but the opposite of sine y for that one. I get the cosine of y for this one, but the opposite of sine y for that one. So those are the angle addition, and out of these spring the double angle identities, because what is 2x if not x plus x? So that if I do the sine of x plus x using this form right here, then I immediately get that the sine of 2x is equal to the sine x cosine x plus cosine x sine x, or 2 sine x cosine x. And now, seeing this, I see that this particle, the product of sine x cosine x, can be immediately referred to as 1/2 sine 2x. And that's the key to unlocking Newton. Meanwhile, the cosine of 2x is going to be cosine x cosine x minus sine x sine x. And if I now directly appeal to the Pythagorean identity, replacing sine squared with 1 minus cosine squared, I get this. Or if I replace cosine squared with 1 minus sine squared, I get this. And from here, I can get the double angle identities for sine and cosine. Okay? So that now needs to become part of your toolbox, and the only way to do that is to talk yourself through it. Probably not sitting bored in English class, because you need a little more concentration. I did for biology, just kidding.
That's perfectly fine.
Computer apps, there you go. That is actually some productive use of time right there, to do some calculus during computer apps. Okay,
Nice.
our main story for today is volume of solids of revolution on washers. We want to consider the same region we've had. But now what we're going to do is creatively revolve our region about various axes. Find the volume of the solid generated when R is revolved about let's start with the x-axis as an axis of revolution. Here is my axis of revolution right here. And I observe that when I make a cut perpendicular to that axis of revolution, that cut goes through some daylight. It is not a part of that region. Everybody see that? This portion is actually part of the region R. There's a distance between them. And the implication of that is that when I revolve this solid around, then this cut is going to go around. And when it goes around, it ends up making a shape that has a hole in it.
This is the one.
It looks like a donut, but it is not actually round at the edges.
What? It's kind of like a weird hourglass, like.
Yeah, it's kind of
Oh,
like,
will this shape make a weird hourglass? The hole will make a weird hourglass shape. The outside will be like a cylinder. Yeah. Possibly so. But the resulting shape here is not a donut shape, but it looks much more like an actual washer like you use to secure a screw. By the way, does anybody know what the purpose of washers are physically? Why do I put a washer?
To like protect it so you can tighten the screw and you're not, there's pressure, but it's not enough to grab the wood.
Yes, that's right. It distributes the pressure out so that when you tighten the screw, you don't end up cracking the surface that you're going into.
Or if in robotics, you might jack something up with washers.
Well, you can also use it as a station. That's exactly right. There's multiple uses. Now, we're thinking in terms of differential volumes, differential elements of volume. Then what we're going to do is to think again that volume dV is equal to area times dx. But the area now is going to be the area of the outside circle, which is going to be pi times r squared here. Take away the area of the inside circle, which is going to be pi times little r squared here. And all of that is times the width, dx. Yes? So if we look at this head on, we have a circle with another circle cut out. And so what we're doing is saying that we have the area of the entire circle take away the inside. The area of the inside. And notice this is the key point so that we don't forget, and this is why we never do curve minus curve. We are subtracting areas and not radiuses. subtracting areas and not radiuses.
What is the area of top curve minus
It's the area of the circle minus the area of the circle.
The top is big R, the bottom is little r.
Specifically, top minus axis is big R, and bottom minus axis is little r.
Oh, we always just have to figure out which one.
Okay?
Probably the
Also, if the axes were somewhere else, you would,
Right. The radius is defined by the axis. Yep. That's it. So in this particular case, if we're revolving about the x-axis, then our big R is going to be the top curve, which is 4, minus the axis, which is 0. The little r is going to be the inside curve. I think of them as outside and inside curves, rather than top and bottom curves. And I'll show you why in just a second. The inside curve, which is x squared, minus the axis, which is 0. And so my volume now is going to be pi times the integral of big R squared minus little r squared dx, all the way from the first x to the last x, which is -2 to 2. And big R is 4 squared. Just a small thing, when you're dealing with x squared, don't forget that you actually have to square your radius still. And we'll let that integral lie. I'm not going to spend time on the evaluation. Well, no, I will, because there's a couple of important points. One is, notice that we have an even function for the integrand. And so we're going to pull off the very common trick of integrating only half and then doubling. And then the second thing is,
Oh, it's 16. It's sweet.
yep. Notice that for very simple polynomials, you can integrate in your head. And that's, let's see, old school, we would actually simplify this. So that would be 2 pi times, let's see, 160 minus 32 is 128. So I get 256 pi over 5. I'm not totally positive that there's value in getting these final numerical answers, but there it is. Very often, these kinds of problems on the AP exam end up being in the calculator section. Question? Okay, so let's take that same region, and now we're going to revolve it about a different axis, and that different axis is going to be the axis y equals 5. So if you can picture the shape that we have here. The shape that we had for x equals the x-axis was a shape that was a cylinder on the outside with a kind of hourglass hole in the middle.
No, it's the other way around.
Now it's more like an M&M with a cylindrical hole drilled out through the center. We have, I think it's called an oblate spheroid, with a hole drilled out through the center. So I have a shape that looks kind of like this, with this hole drilled out through it.
That's so cool.
We're going to use the same concept here because my slices perpendicular to the axis of revolution now look like this. Notice that I start at the axis and then I go out to the outside curve. And my outside curve is the one farthest away from the axis, which is y equals x squared. And the inside curve is the one closest to the axis, which is the line y equals 4. And so I have for my big R, outside curve minus axis. In this case, the axis is above the curve, so I'm going to reverse that. I'm going to do it as axis minus curve, so that I have positive values. However, if you accidentally dork up and do curve minus axis, the squaring obliterates that negative sign, and so it's really hard to mess it up. So,
You can find a way.
right. The inside radius is going to be axis minus curve here, which is 5 minus 4, or simply 1. And the volume is now pi times the integral from, again, -2 to 2, big R squared minus little r squared dx. And I'm going to leave that integral right alone. Hey, there he is. Come on.
Hey!
Come on.
Guys, listen to this guy.
Baby.
I promise you in college you will thank him very much. Calculus will be super hard if you don't listen now. That's it.
That's it, he's
Come,
done.
come tell my Calc 1 students that in spirit. That would be awesome.
That's it?
You should, if you can.
What time is that?
Like 9, 10 or so. What time does this period overrun?
Okay, yeah, I'll be here then.
Yeah.
9:17, right? Is it something?
It would be, but
We're on
it's
the
simply
same
Oh,
Did you get to see the map?
oh no, I haven't done that. I'm about to go there right now.
Cool.
I'll be right back.
Good to see you.
Listen in.
Question. Where did I get to?
Oh, yeah, good. So, we've been dealing with this region so long, I kind of skipped some things. One of the things that we do before we get started is to find intersection points.
Okay.
Yep.
So you just take the intersection points and
Yeah, exactly. Here's what I'd like for you to do. I'd like for you to consider a third solid revolution formed when we take our region about y equals -1 to find the volume of that solid. Go. You can leave your answer in integral form.
We slide back up.
Okay, slide back down.
You said we can use
That's a really weird shape.
that weird. It's like the first one or something. Like this is like the inner. What? It's like a cylinder. Just
There's gonna be a whole thing.
yeah. That's what I said. This is the hole. And the shaded area is the hole.
Is that what this is?
I have followed.
It's tad wider than the first one.
Yeah. Yes. I didn't do the 2 pi thing, but
That's what I got.
Circle.
Yep.
Fine. Pi squared.
I didn't do 2 pi. I didn't name
From
it.
0 to 2.
I didn't name it.
Oh.
Yep, that's what I got.
And you should have
Start breaking up.
something that is equivalent to this.
Yes, yes.
Seems much easier than it.
Then last year?
Than last
Yes.
Last year, yeah.
Yes, it does.
Last year I was just like, which one's the outside curve? I don't know.
Okay, well, let's actually take a look at
That's
one that might be like that.
Yeah.
Let's consider,
Yeah, as long as
I
it's-
watched maybe like 50 videos trying to understand it. And it didn't help that it snowed that whole series when we were trying to go in it.
oh my gosh.
You were just like, I'm gonna put up a video and I hope this helps. And we do the homework and we get through it and then we're like, eh.
Are we open to?
You told me the videos helped.
They did help,
Huh.
but I did better than the homework. It was just
I'd forget about it. Or, wait, do you think we'll have time to do the, x equals ones where you like
Oh,
revolve
before you
around
revolve it this way.
this way?
We're about to.
Jesus.
That,
It is circle day.
It is circle that.
Yes, happy thought. That
That's
means I don't need to
fantastic.
pretend to pay attention.
I don't even pretend to be right.
Maybe we'll buy a pencil something in that.
Nothing else matters until it's done.
Okay, so we have R is the region here in the first quadrant. Find the volume of the solid generated when R is revolved about the y-axis. It turns out in the first quadrant is redundant because
Because it's in, yeah,
it's in the first quadrant.
it's already in the first quadrant.
So we have this guy right here, and we have this guy right here. It's a very small region. Notice that
Take some more.
the curve, no, it's the other way. Above, and that guy goes above. Yeah, like that. I've exaggerated here. If you actually draw this on your calculator, you can hardly tell the difference between the curves. But x cubed is going to be below x squared between 0 and 1. We find the intersection points. And it's fairly clear that the intersection points are at x equals 0 and x equals 1. If it's not clear, factoring is your friend. Okay. And now we're looking for the volume of the solid generated when R is revolved about the y-axis. So for purposes of seeing it more clearly, I'm going to take just this portion of it and blow it up a little bit. Here's my curve y equals x cubed. Actually, here's my curve y equals x squared. Here's my curve y equals x cubed. And now we're taking this about the y-axis so that when I take a cut perpendicular to the axis of revolution, lo and behold, my cut has a width of dy. Sacre bleu, which means sacred blue. I need to-
Isn't that a square word? French.
Well, yes, but it means sacred blue. What's that?
It's really weird things that can get.
Yes.
You know what's bothering me? I've had the radio on this morning, and they said that yesterday was twice as cold today as it is today, and I don't know what that means.
Oh my gosh.
What is twice as
It's
cold?
probably 9 to 18.
I don't know what
I
twice
wish it was
Twice as
18
cold.
instead of 9.
But wouldn't that be twice as?
Which
Today is
Yesterday was
twice as
Christmas.
warm.
the only scale on which that actually makes any sense is the Kelvin scale.
But that would be such a drastic difference.
Yes, it would.
I didn't know what their basis was. To say
It would be 282 versus 291, which is not twice as cold, or twice as anything.
It's really been bugging me.
Twice, it's not
Like,
twice as
the
anything.
standard of cold is
Okay.
like, oh, 32 is-
We need to answer her question or she's going to be a sad puppy. And so we're looking for,
You have to transform into a puppy. Don't answer your question.
I'm a cat person.
we begin with our form here because this focuses our attention. And now we see that we're looking for the outside radius in terms of y, and we're looking for the inside radius in terms of y. And the outside radius is going to be curve minus axis. I start at the radius and I go to the outside curve, which is this guy right here. And I can see that the outside radius is going to be x minus 0. But the only problem with that is that the x is not the right variable. So I go back to the outside curve, and the outside curve is y equals x cubed. And I say, what is x? It is the cube root of y.
I like the one where it gives you x equals whatever y.
Yeah.
It's just really convenient.
I like those too.
Because then you just plug it in.
But I figured I would do one in which that was not the case, because we can't always do what we like. And the inside radius is going to be, again, curve minus axis, which is, again, the x-coordinate minus 0. And this x-coordinate is the square root of it. So that when the dust settles, my volume is equal to the integral, pi times the integral, from the first y, which is 0, up to the last y, which is 1, of the big radius squared, y to the 2/3, that's the cube root of y squared, minus the square root of y squared, which is y.
Whoa,
And that's it.
math.
So this also seems a lot less distressing than it did last year.
Yes.
The only thing that was strange about it
When it gets
was that
harder.
we had to solve for x in terms of y. And the reason we knew we had to do that was because our integral was in terms of y. And the reason we knew that is because we drew a representative rectangle perpendicular to the axis of revolution whose height was dy. So that representative rectangle really controls everything.
That would make a little tricky.
Yeah.
It would make a kind of a bowl shape, yeah, exactly.
Which is really.
That's how I'm gonna design my goals in the future.
Questions, comments, or revolutionary jokes?
I'm gonna use cap.